Oh, wait. It's 11. All right, so I thought I'd start class today with something for you to look at over here. All right, so what I'm going to do is I'm going to bring your notes up, and I'll try and make this a little bit bigger. There we go. Okay, so over there on the board, take a look. I'm going to take a string here. I'm going to hang a string on the board. So let's say here. All right. There we go. All right. Okay. So what does that look like in terms of functions? What function does that look like? Something we've studied before. That look like a parabola to you? Yeah? I mean, it does, right? I mean, all right. So what I have here is I've written a program where I can bring a parabola into the game. So this is the standard form of a parabola. Y equals a times x minus h, that quantity squared plus k. That's what we call the standard form of a parabola. And if you change the a, the h, and the k, then it changes the shape of the parabola. So I'm going to bring a parabola in here. There it is. I'm going to try and control this parabola. And let me mark one thing on here. This is where it's mounted, right? So the part of the string that's hanging, we're not going to pay attention to, right? And I'm going to try and adjust the h and k so I can get that parabola to match up with that string. What do y'all think? Pretty close? You know what I'm going to do here? 0.29. Ooh. All right, so hold on. Let me open up my code. I just want to do something to my code. It'll make this a little easier for me to do.
You made that?
Mm-hmm. Yeah, if you're interested in learning about coding, where is it? Let's go. Yeah, this is it's a C+ based language. It's called Mathematica. Those of you who are familiar with Wolfram Alpha, right? This is when you execute a command on the website for Wolfram Alpha, it's using this program's brains to do the work. Ah, shit. Forgot to hit Shift Enter. Can someone just hit Shift Enter at the same time on my laptop? Oh, well, Shift first, then Enter. Oh, wait, hold on. Let me get you.
You said same time.
Yeah, okay, I think you did it. All right, that'll work. Let me try it again here. Parabola. I should have a little more control over that. Oops. It's pretty close. Oh. I moved it. Pretty close. What do you think? Is it good or not? A little more? I don't know. It seems like I'm off a little bit, right? I mean, it's pretty damn good, but it seems like it's off a little bit. Make this a little bigger so I can try and mess with it a little. Okay, let me try it again. Bring this over, bring this down. Ooh, it's looking pretty good. Oh, wait, hold on. The top's all screwed up now, right? And if I do that, then the bottom's kind of screwed up. Do you see that? The reason is it's not a parabola. Okay? It's not. And that, so if you hang a wire between two poles and you try and model it with the parabola, it's not the correct model. And so that's what kind of today is about. We're going to study hyperbolic trigonometric functions. And I'll show you, I'm going to put the hyperbolic trig function up here. Okay, there's a hyperbolic trig function. I'm going to take the parabola out of here, and I'm going to try and fit this one in there. I wasn't prepared to move it left and right, so what I'm going to have to do is move my whole window. There we go. There we go. Okay, so now let me try and get this thing. Ah! This might take some work. That one looked pretty good, didn't it? So I have a better idea of how to do this. Okay. Do you at least kind of buy the idea that the parabola wasn't that great? Is that okay? Okay. So I'll show you an easier way than me trying to fit this one on top. You feel like grabbing the other side of that? What we'll do instead is we're just gonna put these on these edges. Just put it up here, right there on that, right there. There you go. I'm just gonna let some out. Better? It's still a little off. Look, I mean, come on. All right, it's not perfect. I mean, oh well, hey, hold on, that's really bad actually. I've done this demonstration many times, and it's always right on. That's weird. Oh, well, you're going to have to believe me. That's kind of strange. It might have something to do with the rope itself. Just maybe it's not as flexible as I need. Maybe I'll do that instead. Do y'all believe me yet or no? I mean, I don't want to just not have you believing me. No, you're not sold. I can tell. All right, so let me try and put it right on there.
That's pretty good.
That's pretty good? That okay? We'll see that? All right. So no, if I try and, if I were to leave this up here, I could not put a parabola on top of this. Okay, so imagine that's the rope. Okay, so there's your rope sitting there. If I now try and fit that parabola on top of it, I can't do it. All right, that okay? I'm not going to do any more. So we're gonna be building up to that. That's kind of the end of the section, and we need to now actually talk about what these functions are. So we are going to be introducing the idea of a hyperbolic function, or hyperbolic trig functions. So there are, as you might imagine, 6 of them. And all 6 of these hyperbolic trig functions have something to do with the function e to the x. So sine hyperbolic x. So you can say this, I've heard it said several different ways. I've heard people say hyperbolic sine. I've heard people say sine hyperbolic, and I think everyone can agree that either way you say it, we all understand what you're saying, yes? So what is the definition of the hyperbolic sine? Well, it's right up there. What I want to do is next to this, I want to ask you, what was the definition of sine x? Well, that came from a triangle, didn't it? Like when we were defining sine, we usually did something like, okay, well, if you have an angle and you have the opposite side, which we'll call y, and then we have this hypotenuse, then sine of an angle would be equal to y over h, right? So it was pretty easy to define sine just by using some pictures, yeah? Yes? Okay. Hyperbolic trig functions, we define, you can do some geometric stuff to define them, but the definition is much easier if you just look at it in terms of the exponential function. So this is what? E to the x. Everyone familiar with e to the x? You seen that before? E to the x looks like this if you were to graph it. We're all intimately familiar with this, right? That's y equals e to the x. So it's not just e to the x, it's e to the x minus e to the what? Negative x, and then over 2. And then in the next expression next to it, I split it up and I factored out the 1/2. Now this I did not put up on the notes, but the next step would be to pull a 1/2 out and then you'd get that second expression, right? So e to the negative x, if we were to graph that, I'll graph it on the same axes. This is e to the negative x. So if you were to take these two functions and subtract the 2 and then divide by 2, that graph would be the hyperbolic sine function. All right? So it's some combination of these two exponential functions. And the reason why we study these isn't because, hey, we just want to define this thing this way and let's just have fun with it. It's because this appears many times later on when you're doing analysis in engineering. This expression that involves e to the x and e to the negative x comes up so much that we actually defined a function as being that expression. All right, so it was kind of backwards from what you're used to seeing. Usually we say, hey, here it is, and we'll define it. This way, it's the other way. It's like, oh, wow, that's everywhere. Let's call it something. All right? Now, that's hyperbolic sine. What's the difference between hyperbolic sine and hyperbolic cosine? The only difference is a plus sign. So if I put a plus here instead of a minus, then this thing becomes the cosine hyperbolic function. And then tangent hyperbolic is kind of what tangent was with the regular trig functions. It's the ratio of the sine hyperbolic over cosine hyperbolic. And then secant hyperbolic is 1 over sine hyperbolic, and so on and so forth. So everything else just falls from that. Understand? Okay. Here are the graphs of the hyperbolic trig functions. These are not going to be like your original trig functions, like sine, cosine, where you're going to have to graph these and shift them around, do all that stuff you did in pre-cal. We're just taking a look at them, because what I want you to see is that back with sine, cosine, tangent, like sine and cosine were very, very close to each other, weren't they? They were just like a phase shift off from each other. These don't look anything like that. All right, so there's sine hyperbolic right there. All right, let me extend the domain out, the x range, and y range. Oh, I'm already there. So that's what your sine hyperbolic looks like. There's cosine hyperbolic. Hey, that almost looks like a parabola, right? But it's not. That's that hanging wire one. Excuse me. So the cosine hyperbolic is this almost parabolic. We call that a catenary. And then the tangent hyperbolic looks like this, which kind of looks like which trig function from pre-cal? A little bit like. Isn't that like an inverse tan or something like that? Inverse secant. Remember what tangent looked like? Right? Tangent looked like this. And so if you were to take that function and look at its inverse reflected over the identity, right, a reflection, it would look like this. That's what your arctan looked like. So it's similar to arctan. It's not arctan, but it's similar to it. And then I could go through the rest. It's not important that you memorize what these look like. Again, I'm just showing you that there are major differences between all of these. All right? What we're going to be more interested in is working with them algebraically, because like I said, these things come up later within a problem. The algebra that you need to be familiar with, we need to kind of spend some time on. I feel like I forgot a note there. Oh, here we go. Yeah. So here's the first example for today that I'm going to do on the board. I would like for us to show that this equation is true. All right, so example 1, I want us to show that cosine hyperbolic squared x minus sine hyperbolic squared x is equal to 1. What does that look like? Does that look familiar to you? Yeah? That looks almost like the Pythagorean identity, which was sine squared x plus cosine squared x was equal to 1. And so this order didn't matter, right, in pre-cal, because it was addition. Here we have subtraction, and so the order does matter. And we want to show that this is true. It is true, but we have to show it. So do you remember how you show something is true? How you verify an identity? What's that? Okay, so how do you mean go backwards?
We'll see how you got there, so you got go back.
Okay. Do you remember if you had ever had an equation and you were asked to verify it's true, you started with one side and turned it into the other side? That's basically what we have to do here. We have to pick one of these sides and show it's equal to the other side. And you usually pick the side that's more complicated. So like 1, what am I going to do if I write down 1? How am I going to get it to that? There's not a whole lot to work with, right? 1 is a lot of things. It's 3 minus 2, right? I mean, it's so many different, it's infinitely many things. So let's work with the more complicated side. Try and turn it into 1, all right? So I'm going to write down the left-hand side. We call this the left-hand side, LHS. And I'm going to try and convert that into the right-hand side. So let's see if I can do it. The left-hand side of this equation is cosine hyperbolic squared x minus sine hyperbolic squared x. Now the only hope I have to get it to turn into 1 is to use the definition of the cosine hyperbolic function and sine hyperbolic. So what is cosine hyperbolic x by definition? E to the x minus e to the negative x over 2. That's cosine hyperbolic x, right? But then squared. Plus here. Oh, yeah, cosine, sine, yes. Sine, subtract. Minus e to the x, this one, minus e to the negative x over 2, and then squared again. Now I cannot write equals 1, right? I'm trying to show this equals 1. So all I'm saying is that this is equal to this. And now I continue. Are you okay like that? You sure? All right. So let's square these things, all right? I'm going to have to square a fraction, so I square the top and bottom, right? When I square the top, I think I'll go slow here. I'm trying to do e to the x, right, plus e to the negative x. Squared means times itself. On the bottom, that's easy. 2 squared is 4. And then over here, I'm going to do the same thing, right? And there's a minus sign between them. So minus e to the x plus e to the negative x. I did plus again. Minus itself e to the x minus e to the negative x all over 4 again. We good? And now expand this expression out. So what is e to the x times e to the x? It's e to the x squared, which is the same as e to the 2x, right? X times 2. You multiply the powers. So that first multiplication gives you e to the 2x. How about this one times this one? What's e to the x times e to the negative x? It's e to the e to the 0. Okay, so think about it this way. If I said, what's x squared times x to the negative 2? If you have the same base, you add the exponents, don't you? If you're multiplying. So I do x, take away x. That's e to the 0, but e to the 0 is 1. So that second multiplication here gives me a 1, positive, right? Plus 1? Yes. Now what about this inner multiplication there? Same thing. So plus 1 again. And then the last multiplication, what do I get? Plus e to the, maybe I should write down here. What's e to the negative x times e to the negative x? You add the exponents? E to the negative 2x? Are we all good on this? All right, so e to the negative 2x. That's all over 4 still? Yeah? Then minus, now this multiplication can be a little bit different, just a little bit. When we do this, we get e to the 2x, right? So that's okay, that's not any different. This one times this one, we still get 1, don't we? But it's minus because this was negative and this one was positive. So we get minus 1. And then we do the inner one, we get 1 again, but it will be minus. So minus 1 again. And then the last one, here, it'll be plus, and it'll be e to the negative 2x again, right? All of it over 4. And now we can, well, we have several options on how we could do this. Like, you mean like put the ones together? I don't. Everything's over 4, isn't it? Yeah, right. Everything's over 4. So why don't I distribute the negative through and then just put the whole thing over 4? Yeah? And you'll see immediately what's going to happen. Lots of stuff's going to go away. Okay, so we get e to the 2x. We have plus 1 plus e to the negative 2x. And now I subtract e to the 2x. I subtract a negative 1, so plus 1. I subtract a negative 1, so plus 1. I subtract e to the negative 2x. It's the whole thing over 4. And then you see everything starts getting canceled out here. All the e to the x stuff goes away. So this e to the 2x cancels with this minus e to the 2x. This positive e to the negative 2x cancels with minus e to the negative 2x. And all you're left with is 4 over 4, which is 1. So we verified the identity. Okay? On your homework, you'll be doing a few problems where you'll be doing the same sort of thing. So here are the common identities. You know, in pre-cal, you have like a sheet full of identities, right? There's the same thing for the hyperbolics, but these are the main ones. The first one that you see there, sine hyperbolic negative x equals negative sine hyperbolic x. That means that the hyperbolic sine function is an odd function. Please recall what it means for a function to be odd. This will come up later. A function f is said to be odd if f of negative x equals negative f of x. So that means when you plug a negative into the function, a negative number, let's say, it's the same as plugging in that number but positive, and then just changing the value negative. I'll show you an example of an odd function. How about the function x cubed? That's an odd function. Why is it odd? Well, because let's say I take negative 1 and I cube it. What do I get? Negative 1. Okay, so that would be me plugging in a negative value into the function. Instead, what would happen if I took the positive of that, 1, cubed it, and then made it negative? You get negative 1 also. So they're the same. Sine works that way from pre-cal. What I'm telling you here is that the hyperbolic sine function is also odd. I don't know if that makes sense. Go review this if it's been too long. And then what about cosine hyperbolic? It's an even function. Okay, so what does it mean for a function to be even? It's this. If you plug in a negative, instead of getting the function but negative, you just take that negative away. So it means that if you plug the negative value into the function, it's the same as plugging in the positive. All right, the third identity is the one we just proved. How about the identity below it? 1 minus tangent hyperbolic squared x equals secant hyperbolic squared x. How do you think I could show that identity is true? Like if I were asking you to show this, you could do what we just did, right? You could go and rewrite one of these sides using the e's instead. But if we just proved the first identity, which is the one right above it, if we just proved that, didn't we just prove that? Yeah. Then instead, what we could do is this. We could say we know that cosine hyperbolic squared x minus sine hyperbolic squared x equals 1 because we just showed that, right? Why don't I divide everything here by cosine hyperbolic squared x? So just come in here. The equation we know is true. Divide this by cosine hyperbolic squared x. Divide this by cosine hyperbolic squared x. And then over here, divide this by cosine hyperbolic squared x. You get 1 here minus sine over cosine for hyperbolic is the same thing. So tangent hyperbolic squared. And then 1 over cosine hyperbolic is secant hyperbolic squared. That's actually how, if you go back to your Pythagorean identities, that's how you could get all, there's 3 Pythagorean identities. You can do the same thing. If you remember one of them, you can get all 3 doing the same thing. Make sense? Okay. These are fun. There's a homework problem like this. I'm going to show you the setup, okay, and only the setup. And I think I'm going to do, well, is it, I might have it as the next example. Hold on. No, it's not. Whoa. Come on, Robert. What if we wanted to show let's do the bottom one. Cosine hyperbolic x plus y equals cosine hyperbolic x cosine hyperbolic y, right, plus sine hyperbolic x sine hyperbolic y. So here's my hint to you, okay? I'm not going to do it. We would pick one side, right, and start working through it. We have to convert it over to e's. This one's going to be hard to take one side and turn it into the other. So what I recommend you do, I don't know if you remember ever doing this on verifying identities, you work with one side and you get it to a certain point. Then you work with the other side and you get it to a certain point and you get them to meet in the middle. Remember ever doing that? It's like you work this down, You get it to something, you're like, I don't know about that. Then you work this down, you go, oh, holy shit, they're the same thing right here and here. So you actually have a path that leads from one to the other. That's a way you could do it. So let me help you just at least set it up. This right here is e to the what?
X. Plus
What's the definition of cosine hyperbolic of x? Right? Okay, so instead of x, what's cosine hyperbolic of a box?
whatever's in that box.
Oops, that box. That's right. So this should actually be e to the what? X plus y plus e to the negative x plus y over 2. Right? That's what the left side is. The right side, well, let me do a little more with this just so you can kind of see it. Isn't this right here, this first piece, isn't that e to the x times e to the y? Just this. Same base, different exponents. You add the exponents, right? So this is e to the x plus y. That's this. Plus, isn't this one e to the negative x times e to the negative y? This one. Because if you distributed those two through, you get negative x, negative y, or minus x minus y. So if I put these two back together, I'd be here, and then I could factor a negative out and be here. And then that's all over 2, right? I bet that if you work with this side now, you'll be able to get it to this. But remember, this one, right, just this one, is e to the x plus e to the negative x over 2, right? The next one would be e to the what? Y. E to the y plus e to the negative y over 2. Then plus that over here, e to the x minus e to the negative x over 2, and then e to the y minus e to the negative y over 2, and then you put them all together. I bet you if you do enough massaging of it, you can turn it into that. So that's your homework problems. I think you're asked to do the sine one, but it's the same idea, same concept. All right. So after you've worked with those enough and you start to get kind of comfortable with it, then the next natural question would be, well, what's the derivatives? You know, what are the derivatives of these functions? Right? And here they are. This is going to look familiar. The derivative of the hyperbolic sine function is the hyperbolic cosine function. That's exactly like it was for pre-cal for sine function, right? So we don't have to remember anything new. But the derivative of the cosine hyperbolic, we would hope it would be negative sine hyperbolic, right? Because that would match from pre-cal, or from cal 1. It doesn't, though. There's no change in sign. And that's actually pleasant, isn't it? We're not going to mess up the sign on that ever. The derivative of tangent hyperbolic is secant hyperbolic squared, and then the rest are listed there. And if you have your formula sheets, if you've printed those out and started to bring them to class, these are all listed, right? Are they all? Do you see them there? All 6 are there? So, you know, I'm not even asking you to memorize these, all right? Just know where they come from. But let's at least show one of these is true. Can I at least convince you of the first one? Yes? All right, I'll just convince you of the first one. It's going to be easy. Once you see it, you're going to be like, oh, that wasn't so bad. I'm going to show right now that the derivative with respect to x of sine hyperbolic x is equal to cosine hyperbolic x. All right, that's what I'm going to show. So this really means I need to show that the derivative with respect to x of sine hyperbolic, which is, well, there's different ways to write it, right? But I'll write e to the x minus e to the negative x over 2. Is that okay? I need to show that that's equal to cosine hyperbolic. With me? All right, so I'm going to not take the derivative yet. I'm going to rewrite this in that more convenient form. Well, it's more convenient for me right now to use this form. That's just me pulling that 2 out, right, out front. The reason I want to do that is because if I want to take the derivative here, I have multiplication, scalar multiplication. This 1/2 will just come with me, won't it? When I take a derivative, there's a constant in front of a function. It just comes with me. So I'm taking the derivative right now. The 1/2 comes. And then, since there's 2 terms in here, I just take derivative of each one. The derivative of e to the x is itself. And then be very careful with this one. Minus the derivative of e to the negative x is itself, right? E to the negative x. But then chain rule, derivative of what's up here, -1. And so that negative and negative is going to become a plus. And so you get 1/2 e to the x plus e to the negative x, which is cosine hyperbolic x, right? So all that happened was when we took the derivative of sine hyperbolic, that minus that was in here, because of chain rule in the derivative, turns into a plus.
Oh, you were only working on the left side of it, right?
No, okay, I'm glad you brought that up. I wasn't doing what we did in the previous problem where I was trying, well, I guess I was trying to turn the left side into the right side. Yes, I am. I'm working with one side, and I'm trying to show it's equal to this. Yes. But it's different in the sense that I'm having to take a derivative, right? I'm having to show that the derivative is equal to that. So we didn't do that in the previous problem. And you could go through and do the rest, but yeah, sounds too much like work. All right, let's look at example 2. Does anyone remember from Cal 1 how we showed, I'm not going to do it, but does anyone remember how you showed in Cal 1 that the derivative of sine was cosine? Anyone remember how we did this? You actually had to use the limit definition. You had to use the limit definition of the derivative to do it.
Like x plus h or something.
Yep, all of that. You had to show that the limit as h goes to 0 of sine of x plus h minus sine of x all over h. You did that limit, and then when you did it, you used the sum formulas for sine. You broke it up, and then you used these certain limits that went to 0 and 1, and at the end you get cosine x. Hopefully your teacher showed you that. I know I did in my Cal 1 class. So that's how we did derivative of sine was cosine. And then we did in Cal 1 derivative of cosine is negative sine. But when it came to showing you what the derivative of tangent was, we did not use the limit. What we did instead is we rewrote tangent as sine over cosine, right? And then we use the quotient rule. So we teach you the quotient rule, and then when you take derivative of this, it's derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom square, blah, blah, blah. Simplify it all up, you get this. So it's like once you get those 2 core derivatives, sine and cosine, all the other ones are a result of just product rule, quotient rule, things like that. You could do those others the same way. Once you establish the first 2, the rest of them are just applications of the common rules. All right, so now let's do that example. So y is equal to x secant hyperbolic of e to the x. And we're asked to find y prime. So now you're allowed to use all the rules, right? You have the formulas. You don't have to prove to me what the derivative of secant hyperbolic x is. You know what it is right there. It's just now use your product rule, your chain rule, do all that appropriately. So what do we have here? What rule do you see that we're going to have to address?
Chain rule.
We do have a chain rule, right? The e to the x is inside the secant.
Product
But we also have this product, and the product is the overlying rule that we have to pay attention to, right? So we're going to go, what, derivative of this one times this?
That.
So just this plus, because it's product rule, the derivative of secant hyperbolic of something. What's the derivative of secant hyperbolic of x?
Negative secant hyperbolic of
So I'm going to write negative secant hyperbolic of e to the x, because that's the argument of that hyperbolic function, times tangent hyperbolic of e to the x. I'm running out of room here.
times e to the x.
Times the derivative now. So we're done with secant hyperbolic, right? Sorry, secant. We're done with that. So we go inside and take derivative of what's in there, which is e to the x. And that's, I'm going to put it here. So times now e to the x, and then times x to finish off the product rule. So here's what we get. Our derivative would be secant hyperbolic e to the x. Is this going to be plus or minus here? I think I'm missing a parenthesis here, yeah. A minus. And I'm going to try and put things in a different order. X, so I'm going to bring this out to the front. E to the x. And then next to that, secant hyperbolic e to the x, tangent hyperbolic of e to the x. That's it. And what could you do if you wanted to? You could factor secant hyperbolic of e to the x out. You could, right? But that's no more correct than this is. Any questions on where any of these pieces came from? So hopefully you're feeling good about derivatives. I don't think I mentioned this on the first day, but what is the importance of you being good at derivatives at this point? So like if you got through Cal 1 and you're like, but I really never got chain rule. Chain rule was always this thing that, just kind of this cloud over my head. The problem with that is Cal 2 is backwards chain rule. So if you're not good going this way with it, it's going to be nearly impossible to go backwards. Or it'll be much easier for you to go backwards when you recognize things. And the only way that happens is if you were comfortable with chain. All right, moving on. Yeah? No questions? All right, so I'm just going to list something out here. Sine x, cosine x, tangent x. Don't worry about copying this down, okay? We have cosecant x, secant x. We have cotangent x. Those are the 6 trig functions from pre-cal, right? Do we know derivatives of all those? Yes. Okay, then we have all the inverse trig functions. We did those last class, right? And then we looked at the derivatives of each of those, didn't we? Yeah? Today, we've introduced 6 more hyperbolic trig functions. And we just talked about the derivatives of each of those, right? So what's naturally going to be next?
The inverse.
The inverses of the hyperbolics and the derivatives of those. And so at the end of the day, we will have, 4 groups of trig functions with derivatives for each one. So a total of what?
24.
There's 6 here, right? 6 here, 6 here, 6 here. 24 trig functions plus their derivatives, so another 24 functions that are their derivatives. Okay. We'll have a quiz next class. You'll just, nothing. You can't use any formulas. You're just going to have to put all 24 with all derivatives. You want to do that? No. No, we won't. We don't want to do that. All right. So let's look at the inverse hyperbolic trig functions first. Let's just look at them, and then we'll talk about their derivatives. So please remember that last class when we were talking about the inverse trig functions, not hyperbolic, we had to make certain domain restrictions, didn't we? And it's the same thing for the inverse hyperbolic trig functions. There are certain domain restrictions that we have to make. I'm only listing 3 of the inverse hyperbolic trig functions because the others are in the book. Well, I don't even know if they're in the book, to tell you the truth. But they're not used that often. So that's why I'm only showing you these 3. So that's the definition of the inverse. This is it right here. And you might be asking yourself, how in the world did they come up with this? And it just looks like crazy math that somehow they just came up with it, right? So this is Cal 2, so we're going to show where it came from. So we want to show, look, what I've been doing here with showing you stuff, and I told you that some of this is in your homework, right? This one right here is not necessarily something you would see on a test or in a homework problem. Yeah, as a homework problem. This I'm going to show you because the math in here is pretty cool. And you may not have ever seen it before. So I think it's worth seeing. Let me pass the sign-in sheet around. Is that my phone? Oops, I thought I silenced it. Would anybody like, I'm just silencing my phone. Anybody want to remind me how we figured out what the inverse sign was? And remember, we're not doing a derivative here. Okay, so you do like a regular sign on both sides. Now, that is correct, but be careful on that, only because you're saying times, it's not times, you're actually taking sign on both sides. Okay. All right, so there's an idea. We could take sine on both sides of this, couldn't we? If we do, the problem, let me do it, but maybe don't write this down. If I take, I forgot the hyperbolic, didn't I? Oops. Forgot my little h in here, sorry. If I were to take sine hyperbolic, right, on both sides of this, what could we assume the left side would become? X, right? And the right side would be sine hyperbolic of natural log, and that would be a disaster right there. It traps that natural log in there. It's really kind of a mess. So I want to take you back to college algebra, because I think there might be a disconnect right now. Let's say I gave you this right here. Y is equal to 2x plus 1. So we're going back way old school, back when math was easier, right? And I ask you to find the inverse of that function. Or maybe we wrote it this way. We said find the inverse. Do you remember these steps?
Yes.
We replace f of x with y, switch x and y, and solve for y. Do you remember that?
Yeah.
So I would now go and subtract 1, and then I divide by 2, and this is the inverse function. Show of hands, how many of you now remember that method? Yeah? So if someone gives you a function, you're trying to find the inverse, what you do is you say y is equal to the function, you switch the x and y's, and you solve for the y, right? So what I'm going to try and show you here is that the inverse of the hyperbolic sine function is this. Okay, so let me start out with the original function. Sine hyperbolic x, right? That's the original function. I'm trying to show you that its inverse is that. So I'm going to replace f of x with y. Are you all with me on that? That's pretty clean. switch x and y. And then finally, solve for y. How are you going to solve for y? You could say take the inverse hyperbolic sine, but that's what you're trying to find. So you can't, it doesn't exist yet. You know what I'm saying? So how do you solve for y? And this is where the math is going to be very, I think, I guess we could say beautiful. I don't think anyone here would take offense to that. I can use beautiful to describe math in here without anyone freaking out. Magical? Okay, well, I don't know if magic, I guess we associate magic with something that's not real, illusion, something. We'll stick with beautiful. Okay, what is the definition of sine hyperbolic y? By definition. It's e to the y minus e to the negative y over 2. Agreed? And I'm trying to solve for y. Can anybody help me get y? So natural log is the thing that usually comes in, right? People are ready to throw the natural log in here, which is correct because natural log and e, they like to play together, right? They cancel each other out. But you have to be careful how you apply it, all right? Could I just do natural log on both sides of the equation right now? I can't do it because, look, I agree with this. Natural log of e to the x is x. That's something from college algebra. But natural log of two things like this, you do not apply to each one. If there's multiplication here, you can split it into two logs, can't you? But if there's subtraction or addition, you cannot split it up. That's a fundamental principle from college algebra. So we're kind of close, but not really. And it's going to become a huge problem that we can't do that. All right, so how about, let me try this. You're on the right track with natural log, all right? You're on the right track. I'm going to keep trying to lead you here. There. You're trying to solve for y. Every time I do this problem, I always like to give somebody an opportunity to either show me they've seen something like this before, to show off a little bit that they know their stuff. Anyone know how you would solve that for y? Anyone want to take a shot at what you could do at this point? You want to get a common denominator? Yes and no, but a little variation of that. How about we just clear the fraction? Okay? So like this is in the denominator. How about we just multiply everything through both sides by e to the y? Is that fair? So 2x times e to the y is 2x e to the y equals, what's e to the y times e to the y? E to the 2y. And then minus, what's 1 over e to the y times e to the y? Minus 1. Is that okay? You still can't do natural log. All right, so I don't want to eat up too much time on this, but I want to see if you remember this. Do we have a formula to solve quadratic equations?
Yes.
It's called the quadratic formula, right? And we would always say that x here is the variable, right? X is the variable. A, B, and C are what? Usually numbers, right? The coefficients of these things are numbers. Look back over here. I'm going to move everything to one side of the equation, to the right side. Everyone agree that that's everything moved to the right side? That's the same equation as this one? Now do a u substitution. What is my u substitution going to be?
U squared
So close, close. So this is the first time you may have ever seen this. You're right, u substitution. The u I'm going to use is e to the y. So I'm noticing that I have e to the, this is 3 terms, right? So it's trinomial. I notice that this right here, e to the y, if I square it, I have e to the 2y, don't I? So if I make a substitution, u is equal to e to the y, then this is going to be u squared minus 2xu minus 1, right? But the x is the thing that you've never had before. It's always, this a, b, and c has always been a number, hasn't it? So I have u squared minus 2xu minus 1 equals 0. And so the number out in front here, 1, that's your a. Negative 2x is your b, and that's the part you've never really had that. And then this right here is your c, and you can apply the quadratic formula, can't you? But instead of using this formula with x's, it's u's, isn't it? So according to the quadratic formula, the solutions to that equation should be u equals negative b plus or minus the square root of b squared minus 4ac all over 2a, right? What's negative b for us? 2x, right? It's the opposite of negative 2x. Plus or minus square root b squared. 2x squared, well, negative 2x, right? Squared, which is 4x squared. Yes? Minus 4 times a times c. 4 times a times c, so negative 4, but we're subtracting it, so plus 4 all over 2. Yeah? Y'all see that? So what I'm trying to get you to see is that I don't think that you've ever solved a quadratic equation when you had 2 variables in the equation. It's always been 1 variable and a bunch of numbers, right? You actually had 2 variables within this equation, but you were able to make it look quadratic and use the formula. Can I pull a 4 out of here? And then that 4 comes out as a 2? And then everything has a 2? So I reduce everything by 2? Over 1, right? So I don't need that anymore. Is that where we are? Is this where we are? What were we trying to solve for again? Trying to solve for y, weren't we? Y is not here anymore. But we made that substitution. What was u? E to the y, right? So I'm going to now replace that with e to the y. Right there. And now you can get y out of here by taking the natural log on both sides. Right? So take the natural log on both sides of this equation, and you get what? Natural log of e to the y is y, and then the natural log of the right side. And is that what we have up there? It's a little off. What's off? It's plus or minus here, but up there it's only plus. So let's look at why it couldn't be minus real quick. If you just look at, just x minus the square root of x squared plus 1, all right? I'd like to know about this thing right here. Remember, for natural logs, I have to be plugging in positive numbers, right? Or else I can't do the natural log. So when I look at this expression right here, my question is this positive or not? Well, in other words, move this negative part over. Is this true or not? Is that true or not? What is the square root of x squared? What is the square root of x squared going to be? Just x, right? Okay, is x bigger than